So let's talk now about reaction enthalpy. It's the change in enthalpy that's associated with a reaction. Okay, so and delta H with the R subscript between the delta and the H is called, that's the official symbol for reaction enthalpy. You might see that symbol written as delta H RXN. Okay, so RXN is abbreviation for reaction, or you might see it as delta H RXN in between. But I'd like you to be familiar with this way of writing it, because that is the way it's tabulated in handbooks. Okay, so that's a standard abbreviation symbol for reaction enthalpy. So reaction enthalpy is just the difference in the enthalpy of the products and the reactants. So imagine a fictitious process where you start out with your reactants separated from each other, okay, and then you mix them, and then the reaction happens, you make your products, and then the products are separated. So if you calculate if you were able to get the H for the separated products, you subtract the H for the separated reactants, that's called your reaction enthalpy. Okay, that's a fictitious process. For practical purposes, we can say that the delta H for that is in fact essentially the heat of reaction at constant pressure for some reactions. Okay, and that's why we give that symbol delta H of reaction it's synonymous with the heat of reaction. Delta H is synonymous with heat of reaction. Okay, let's clarify that. Okay, like I said, the delta H, the reaction delta H, the reaction enthalpy, okay, is equal to the enthalpy of the separated products, okay, minus the enthalpy of the separated reactants. But since enthalpy is a state function, okay, even though this doesn't actually happen, okay, you can just imagine it happening. What we can do is, like we did, what we do is we go to the lab and carry out this reaction right here in a calorimeter, okay? When you mix your reactants, you get mixed products in an insulated container. Q for that is 0. So delta H for that step is 0. Now you imagine that you let your products go back to the original temperature of the reactant. So temperature has changed from T1 to T2 as a result of the reaction. Now imagine taking the products from the mixed products from the final temperature to the original temperature of the reactants. And we said in an earlier lesson that that is your heat of reaction, right? Now imagine one final step where you unmix those products to get separated products, okay? The Q for that last step is going to be 0, okay? Only for reactions where the limiting reactant is 100% consumed. In other words, for reactions that pretty much go all the way to completion. Why is that? Well, imagine the reverse of this process right here. Instead of unmixing the products, okay, imagine the process where you're mixing the products. If the reaction goes all the way, what happens if you mix the products? Nothing, right? So delta H for the mixing here would be 0, so Q for the unmixing would be equal to 0. But that's only true if, in fact, the reaction goes all the way. In other words, if the reaction goes all the way to the product side, what you're saying is the likelihood of products reacting to give you back your reactants is very low. So the delta H for the unmixing, for the reverse process is going to be 0. Okay? So if you look at this diagram that we have right here, we can say that the delta H for the reaction, okay, the reaction enthalpy is Q1, which is 0, plus what we call the heat of reaction, which is minus C delta T, right, plus Q of unmixing, which is 0. So that's why we're saying that this, for practical purposes, we can say for as long as we're dealing with the reaction that goes all the way to completion, the reaction enthalpy is just equal to the heat of reaction at constant pressure. Okay. So a thermochemical equation summarizes what happens during a chemical summarizes the energy changes that accompanies chemical reactions. Okay, so a thermochemical equation is a chemical equation that has attached to it the value of the delta H associated with that reaction. Now, if you see that superscript 0 there, that means you're dealing with a constant pressure, assuming a constant pressure of 1 bar. Now, the old standard is pressure is 1 atmosphere, which is about 1% higher than 1 bar. Okay, most freshman chemistry textbooks still use 1 atmosphere as a standard pressure, but the modern standard pressure is 1 bar. Okay, so if you see that superscript 0 next to the delta H, that simply means you're dealing with a process where the constant pressure happens to be 1 bar or 1 atmosphere. It's pretty much the same, just a 1% difference. Okay, so in a thermochemical equation, not only must you specify the delta H, you also specify the physical states of the reactants and products involved in the reaction. Here you have two reactions which look the same, right? H2 plus O2 gives you water. But here you have two different delta H values. Why is that? Because this particular reaction here, the first one listed, has liquid water as the product, whereas the second one over here has gaseous water as a product. So the delta H that's associated with the reaction enthalpy, depends on what the physical states are for your reactants and products. So you must include physical states of reactants and products for your thermochemical equation. S for solid, L for liquid, G for gas, AQ means aqueous solution, right? Now, if you have a solid reactant or product, and that reactant or product, that solid, is known to exist in more than one form, you must specify the form. For example, carbon, solid carbon can be in the form of graphite, or it can be in the form of diamond. So you have to specify what form it is. Now, if you just say carbon solid, okay, then we are going to assume that refers to the solid, the most stable solid form, okay, at 1 bar pressure. And unless otherwise specified, we're looking at temperature of 298 Kelvin. Okay, so unless otherwise specified, we're imagining that we start off with reactants at 298 Kelvin and end up with products at 298 Kelvin. So that's how you would interpret your thermochemical equation. Now, oftentimes you'll see this subscript R dropped from a thermochemical equation. Okay, so you might see this thermochemical equation without that R down there. And it's okay because it's attached to a chemical or thermochemical equation. It's obvious that that delta H refers to that particular reaction. So it's okay to, if it's obvious that you're referring to the reaction, you can drop the R subscript. Okay? And oftentimes you also just drop that superscript 0. If you don't put that in, it's okay. We just assume you're dealing with 1 atmosphere. Okay? So consider the hypothetical reaction here, represented by this hypothetical thermochemical equation. What's the delta H for a reaction where 0.9 moles of X is consumed? The number that you attach here, okay, this corresponds to the situation where 3 moles of X are involved, 1 mole of Y is involved, and 2 moles of Z are involved. In other words, that corresponds to the moles involved in your balance equation. So it's negative 75 if 3 moles of X and 1 mole of Y were consumed and 2 moles of Z were produced. But what if you have a reaction, you carry out one in the lab, and it's only 0.9 moles of X consumed? What would you have to do? Well, these are all directly proportional quantities, so you can just say 1. You can just use a conversion factor, okay? So you can say, if only 0.9 moles of X are consumed, I can just do a conversion here. I can say, well, it's going to involve, so our delta H for this would be negative 75 kilojoules for 3 moles of X, right? Times 0.9 moles of X. So that's all you have to do. It's really saying it's negative 75 for 3 moles of X, or you can say it's 25 kilojoules per mole of X, right? So our delta H in this case is how much? Negative 22.5 kilojoules. Okay, and 2 sig figs, so negative 23 or negative 22 kilojoules. Right. Let's look at this question right here. You have a hypothetical reaction, 2A plus B yields C. You did an experiment, you measured the heat of reaction, and in that particular experiment you consume 0.2 moles of A. All right? And your heat of reaction was negative 5.0 kilojoules. So if you were to write the thermochemical equation, what would be the value of X in this thermochemical equation? It's not going to be 0.2. Why? 0.2 corresponds to, it's not going to be negative 5. Why not? Because negative 5 would imply that you only lost 0.2 moles of A, right? But this balance equation says, I want the value of delta H if 2 moles of A were to be consumed. So what do? You just say, okay, if I want it for 2 moles of A, delta H for 2 moles of A, then what's the ratio? It's negative 5.0 kilojoules for 0.2 moles of A. Right? So that cancels out moles of A, which would be 50. Okay, negative 50 kilojoules. Okay, now this 2 right here, this is a coefficient in the balance equation. You treat that as an exact number. So infinite sig figs there. All right, so negative 50 kilojoules. Here's another way of looking at it. What is negative 5 over 0.2? $25? Or, yeah, that's 25 kilojoules per mole of A. Right? Negative 25. It's like saying for every mole of A, if it's negative 5 for 0.2, if I divide this, I said it's saying that for every mole of A, it's going to involve negative 25 kilojoules. So, however, so this is for every mole. So if I multiply that by the number of moles in my balance equation, then that will give me the number that I have to attach to my balance equation. So your thermochemical equation here is going to be equal to 2A plus B yields, what is it? C. And the delta H that you attach here is going to be equal to negative 50 kilojoules. Okay? So that's how you interpret a thermochemical equation. Let's try this one. What is the reaction enthalpy for the combustion of 4 moles of H2 gas? So what's our delta H? Okay. It's 4.0 moles of H2. Okay. And you're given this thermochemical equation. What does this thermochemical equation tell you? That the delta H is negative 571.6 kilojoules for how much H2? For 2 moles of H2. But I want it for 4 moles of H2. So what should be the answer? Twice as much, right? And the way you work it out, you should say, okay, it's going to be times negative 571.6 kilojoules for 2 moles of H2. So you can solve this just like your regular stoichiometry problems. Okay, the coefficients and the delta H value are directly proportional quantities. Okay, so here moles of H2 will just cancel out. So that should give you twice as much. What's 571.6 times 2? 1,143 kilojoules. Okay, 3 sig figs here, so 1140 kilojoules. Okay. Or 1.14 times 10 to the third kilojoules. All right. What if your, oops, error here. I meant to have grams of H2 here. Okay. What is the reaction enthalpy for the combustion of 6.06 grams of H2, given this thermochemical equation? I know it's negative 571.6 kilojoules for 2 moles of H2, right? And what did we learn last time? This basically gives you, this number will give you per mole of H2 if you divide by 2, right? So you multiply by moles of H2. Do I know moles of H2? Do I know how many moles of H2 I have? But I know grams. How do you change grams to moles? 6.0 grams of H2. Change it to moles. What would it be? 1 mole of H2 is how many grams? Periodic table. It's 1.008 grams per mole, molar mass of H, times 2. So that's going to give you 2.016, right? So 2.016 grams of H2 in a mole of H2. So grams cancel out. So if you multiply this, what do you get? 6.02 divided by 2.016, that gives you 2.99, that's about 3 moles, times negative 571.6 divided by 2, so negative 854. Okay. So the answer here is negative 854 kilojoules. Okay? All right. Let's talk about bomb calorimetry. When did I mention bomb? In an earlier, the last lesson we did what? Bomb is a fixed volume reaction vessel. Okay? So in a bomb calorimeter, you're doing a reaction at constant volume. So if you remember, we said in those cases, Q, the heat of reaction, is going to be equal to delta E, not delta H. Okay? So delta H then, if you wanted to know delta H, you can actually calculate it from delta E, but then you have to add delta PV. So you should have some information about what delta PV is. Okay, but what's delta PV? It's P final, V final minus P initial, V initial, right? But it's constant volume, so if volume is constant, so V final and V initial are going to be the same. I'm just going to call that V, right? V is equal to V final is equal to V initial. I can factor that out. So that's V times P final minus P initial. So that's just V times delta P. So if you have a way of knowing what V delta P is, you can calculate delta H. So you have to add that to your bomb calorimetry information. Well, if you're in a bomb calorimetry, pretty much the change in PV is going to be a change in the moles of gas. Okay? So you can assume ideal gas law, PV equals nRT. We're going to be assuming remember when we're calculating heats of reaction and delta H of a reaction, we're assuming a fictitious process where you start out with reactants at a given temperature, which is 298 Kelvin, 25 degrees Celsius, unless otherwise specified, and you end up with products also at the same temperature. So temperature is constant, pressure is constant, so volume is constant here. So delta PV will just result from a change in the number of moles of gas. Okay? The change in pressure inside your bomb will result from a change in the amount of gas you have in your bomb. So delta V times delta P, which is delta PV, will just be delta N gas times RT. Okay? So that's delta N gas times RT. So that delta N sub G, there's change in the moles of gas. Let's illustrate that. Let's say your standard reaction enthalpy for this reaction let's say you did this reaction in a bomb calorimeter. So you found your delta E for the reaction to be X. Remember, the heat of reaction, if you're doing it in a bomb calorimeter, is equal to delta E, not delta H. So how would you get delta H for this one? Delta E is equal to delta, what was it? Delta H. That's the equation. Delta H is delta E plus delta N RT, right? Oops, sorry. Remember we said H is equal to E plus PV. Okay. So that's the definition of enthalpy. So delta H is delta E plus delta PV. So that's delta E plus delta N gas times RT. What's our delta N gas here? So our delta E is X, delta N gas times RT. What's our delta N gas? How many moles of gaseous products do you have? What's the coefficient of CO2 gas? 1, right? Water is a liquid, so you don't count that. So 1 mole on the product side. How many moles of gas do you have on the reactant side? You have 1 mole of methane gas, 1 mole of CH4, 2 moles of O2. So that's 3, right? So our delta N gas, we say, is equal to 1 on the product side and 3 on the reactant side. Is equal to -2. So that's going to be -2 RT. So the answer to this question is, whatever delta E is, you subtract 2 RT. That will give you the delta H. Okay? So when you measure heats of reaction in a bomb calorimeter, you add delta N gas times RT to that. That will give you the delta H. Okay. Some limitations of calorimetry, like I said, it's not going to work for all reactions. Okay? Okay. First of all, reactions have to be fast. Why? Well, if it takes 1,000,000 years for the reaction to happen, you can't do it in the lab, right? So it has to be fast, and also, even if it doesn't take 1,000,000 years, let's say it just takes days, then that's still going to be a problem because it's very hard to maintain perfect insulation. Okay, so you don't want to have to worry about that heat loss. So you want to make sure your reactions are fast. Reactions must be complete. That means your limiting reactant has to be consumed completely. Otherwise, you wouldn't know how much reaction actually happened, right? You have to do an extra step to figure out what else, how much product did you make, how much reactant did you consume, and more importantly, that Q for the unmixing, that last step we talked about earlier, will not be equal to 0 if it doesn't go to completion. Okay, so you cannot equate your heat of reaction to either delta H or delta E. So another condition is there must be no side reactions. Well, because if there's side reactions, then you wouldn't know what that overall heat measurement you made is related to. How much of it is due to this reaction? How much of it is due to the side reaction? So these are some of the limitations of calorimetry. It's not suitable for every reaction. So what do we do? If a reaction is not suitable for calorimetry, we have to use our imagination. Okay? We take advantage of the fact that H is a state function. We use what's called Hess's Law. Hess's Law, like I said, Hess's Law basically says that if the delta H for a reaction cannot be determined by calorimetry, you can imagine a series of reactions that will eventually convert your reactants to your desired products, and simply add up the delta H for all of those steps. So this is the significance of defining of H, okay? Because H is a state function. If there is a reaction for which you do not know, you cannot measure delta H directly. You can try to figure it out in terms of other reactants that you can measure, other reactions that you can measure. Okay? So since H is a state function, you can do that. And if you know the reverse of a reaction, if you can measure the delta H for the reverse of a reaction, that's just the negative of the delta H for the forward reaction. Okay? So if going from A to B generates 5 joules of heat, then you would expect going from B to A to absorb 5 joules of heat. Okay? So those are consequences of H being a state function. So also, if H is an extensive property, it's proportional to the amounts of reactants involved in the delta H will be proportional to the amounts of reactants and products involved in the reaction. So you use twice as many reactants, you consume twice as many reactants, then that means your delta H will be twice as much. So if you adjust your coefficients in your balance equation, you can do the same adjustment to your delta H. So let's illustrate that with this example, a few simple examples here. So if A plus B going to C, the delta H is X, what's the delta H for the reverse reaction? Negative X. Okay, so for example, if X going to Y, delta H is equal to negative 3 kilojoules, what's delta H for Y going to X? Negative of negative 3, which is positive 3 kilojoules. So you reverse a reaction. So if you could measure this, okay, and you could not measure this, it doesn't matter. If you can measure this, all I have to do is imagine flipping it, and I just get the opposite delta H. Okay. How about this one? A plus B gives you C, and delta H for that reaction happens to be, let's say, X. Well, if I change my coefficients to 3, 3, and 3, what would be my delta H? 3X. Okay. If 1 mole and 1 mole to give you 1 mole gives you X, then if I triple the amounts, 3 moles instead of 1 mole, I triple the delta H. How about this one? A plus B gives you C, delta H is X. What would be the delta H for this reaction right here? Negative X? Negative 2X. Why negative 2X? Because I flipped it. When I flip it, it becomes, so if I just say C gives you A plus B, delta H would be negative X, right? But here, not only did I flip it, after I flipped it, I multiplied all the coefficients by 2. So delta H for this would be negative 2X. How about this one? A plus B gives you C, and then C gives you D plus E. Delta H for this step right here is X. Delta H for this second reaction is Y. What's the delta H for this reaction down here? What happened here? A plus B became C, and then C eventually became D plus E. Right? So A plus B eventually becomes D plus E. So you can imagine this as occurring as a series of 2 steps. The first step, A plus B first turned to C, and then C turned to D plus E. So what's the delta H for this one? It's just going to be X plus Y. That's what Hess's law is all about. Okay. Let's look at some real reactions. Okay. Let's say I have the reaction of graphite with oxygen gives you CO2 gas. You can measure that in a bomb calorimeter. This is a combustion reaction. Remember, combustion reactions are reactions with oxygen, gives you the oxides, right? So the oxide of carbon is CO2. That's an easy reaction to do in the lab. You can do that with bomb calorimetry. So let's say you determine that to be X. Carbon monoxide gas. You can get a tank of carbon monoxide, introduce that into your calorimeter. You can mix that with oxygen, burn it up. Okay, you can get carbon dioxide as well. Okay. That reaction can also be measured in the lab. So let's say you can measure that, you found that to be Y. Okay, so those are known. Now, I want to know, based on these 2 numbers, can I calculate delta H for this? This one gives you graphite plus oxygen to yield carbon monoxide. Now, why might I have trouble doing this in the lab? I'm actually measuring the delta H for this reaction in the lab. The reason is, anytime you have burning carbon, okay, there's a possibility you're going to get carbon monoxide or carbon dioxide, and if you don't have enough oxygen, chances are you're going to get a mixture of carbon monoxide and carbon dioxide. There's no way you can say that I'm going to control the amount of oxygen and just get carbon monoxide. You'll always get a mixture. Okay, some of the carbon might be left unburned if you don't have enough oxygen. Okay, So that's very hard to control. It's very hard to control whether you're going to get, it's very hard to just say you're going to get carbon monoxide. But how can you guarantee that you don't get carbon monoxide? Like this one. I told you earlier, this one's easy to do in the lab. You can guarantee that all your products are carbon dioxide, that there is no carbon monoxide by using a large excess of oxygen. Okay? So in a bomb calorimeter, you use a large excess of oxygen. You're not going to get carbon monoxide. You're going to get carbon dioxide as a product. So this can be measured easily. This one can be measured easily, but this one cannot. But you can figure out the delta H for this reaction based on these two. How are you going to do that? Let's see. Imagine, okay, my goal is to get a reaction where I start off with graphite, 2 moles of graphite, and 1 mole of O2, and end up with 2 moles of carbon monoxide. Well, which of these two reactions up here has graphite on the left-hand side? A mole of graphite on the left-hand side. This one, right? So maybe what I can do is I'll imagine burning graphite so it becomes carbon dioxide. So I'm going to say my first reaction would be graphite plus O2 gas gives me carbon dioxide gas. But I need 2 moles of graphite. So what should I do with this reaction right here? Double it. Multiply all the coefficients by 2. What's my delta H for this one? Well, the delta H for the original reaction with just 1 mole each would be X. So if I double all the coefficients, what's my delta H for this one? It's going to be equal to 2X. All right? Now I'm going to say, okay, I don't want carbon dioxide. I want carbon monoxide. I want carbon monoxide as a product. I want this on my product side. So what should I do? Well, I made my carbon dioxide from the first step, right? So now I'm going to imagine that the reverse of this second process actually happened. It's not going to happen, but I can imagine it happening. What would be my delta H for that? It's just going to be the negative of this one, right? So if I flip that, I'm going to get negative of the original delta H. Okay, I want to make 2 moles of carbon monoxide, so that's good. I want to make 2 moles of carbon monoxide right here. So I'm going to flip that second reaction. I'm going to say, I'm going to change my 2 moles of carbon dioxide. 2 moles of carbon dioxide. I'm going to flip that reaction to give me 2 moles of carbon monoxide gas plus O2 gas. And so the delta H for this second step is going to be negative Y, because the delta H for the original reaction is Y. I just flipped it, right? So let's combine these two reactions. Now, does that give me the overall reaction I want? Well, I've got 2 graphites right here, 2 graphites right here, and I've got the 2 carbon monoxides up here, right? What happens to my CO2? I made 2, I lost 2. So CO2 does not appear in the overall reaction. What happened to my oxygen? I started out with 2 moles. I ended up with 1 mole, so that means I've lost 1 mole. So that's just 1 mole of O2 left. So I got the reaction I want. So the delta H for this reaction is equal to what? 2X plus negative Y, which is just 2X minus Y. Okay? So that, in essence, is what Hess's law is all about. So the answer to this one is 2X minus Y. The answer would be B. Okay? Now, it's not going to be convenient to list the delta H for every possible known reaction, because it's going to take a lot of, especially in the old days when you have to put everything on paper, right? So as a matter of convenience, okay, chemists have defined what's called the standard formation enthalpies, which so all you have to do is list the substances, and for each substances that we know we can list a value of the standard formation enthalpy for that substance, and we can use those numbers to calculate delta H for any reaction that involves those substances. Okay, so standard formation enthalpy refers to the delta H. If you imagine that you're going to make 1 mole of something, okay, from the elements in their standard state, the delta H for that reaction is called the standard enthalpy of formation. And you see that F right there, that stands for formation. Or you can also see that written as delta HF after the H. Okay? So the delta H of formation refers to the delta H of reaction in the case where you're making a mole of whatever substance you're interested in from the elements in their standard state. What do we mean by standard state of an element? That's the most stable form of the element at a particular temperature. Unless otherwise specified, we're just going to be dealing with room temperature, 298 Kelvin. So for example, the most stable form of oxygen is O2. Okay? The most stable form of nitrogen is N2, it's diatomic molecule in the gas phase. So, like I said, values of standard formation enthalpies are tabulated to facilitate calculation of delta H for any reaction. Okay? And how are you going to do that? Well, before we show you how it's actually done, let's look at this one right here. Let's see if we get the definition of standard formation enthalpy down. Okay, so for which of the following is the delta H of reaction equal to the delta H of formation of NH4Br, ammonium bromide solid? Is it A, B, C, or D? All right, so let's see. What's the definition of standard formation enthalpy? That's the delta H for a reaction where you make 1 mole of whatever it is you're interested in. So which one can you eliminate right here? C. This is 2 moles, so that's wrong. Okay? And you're making it from the elements in their standard state. Okay? What's the standard state of nitrogen? Most stable form of nitrogen gas is N2 gas, right? So this one is wrong. What's the most stable form of hydrogen as an element? Standard state of hydrogen is H2 gas. So this one is wrong. Okay? What's the most stable form of bromine? Br2 is also diatomic, but it's a liquid. Okay, so this one is wrong. Okay, and this one is wrong. That's Br2 gas. And so, what's the correct answer here? D. And let's just make sure it's correctly balanced. 1/2 times 2, that's a mole of N2. You have 1 N2 on the right side. 2 times 2, that's 4 moles of H. You have 1 mole of N on the left, 1 mole of N on the right. 4 moles of H on the left, 4 moles of H on the right. 1/2 times 2, that's 1 mole of bromine on the left, 1 mole of bromine on the right. So your equation is balanced. Okay, so the delta H for this reaction, reaction D, is what we would call the standard enthalpy of formation of NH4Br solid. Okay, let's look at this. For which of the following is the delta H of formation equal to 0? N gas or N2 gas? I lost my clicker again. Ready? Let's see how we're doing. Okay. B is a popular answer. Okay. You have a chance to change your answer before I close it. Okay. Correct answer is B. YB. Oh, I have to stop it first. YB. Okay, what's the delta H of formation of N? It's of making of 1 mole of atomic nitrogen from diatomic nitrogen, right? So to balance this equation, that would be that. What's the delta H formation of N2? I have to make a mole of N2 gas from what? From a mole of N2 gas. So delta H for this second reaction right here is going to be 0. How do you make a mole of N2 gas from a mole of N2 gas? Do nothing, right? So delta H should be 0. How do you make a mole of nitrogen atoms from half a mole of nitrogen gas? You have to break those bonds, right? To break bonds, you need energy. So delta H for this is in fact going to be a positive number. So it's going to be an endothermic reaction. You have to pull apart those nitrogen atoms. Okay? So for which of the following is a standard delta H of formation equal to 0? In other words, what did we just learn in that earlier question? When you're dealing with elements in their standard state, the delta H formation has to be 0 because you'll be forming it from itself, which means doing nothing, right? So, in other words, a way to rephrase this question is, which of the following is an element in its standard state? Is it I gas, I2 liquid, I2 solid? Let's see if you remember. What's the most stable form of iodine? Under ordinary conditions. Correct answer is okay, C. B. Okay. The most stable form of iodine is a solid. Let's do a Google search for iodine crystals. That's your iodine crystals right there. The most stable form of iodine under ordinary conditions. Pure iodine is a solid. You mix it with alcohol, you get tincture of iodine, which you can use as a disinfectant. That iodine you have in your biology lab is a tincture of iodine. It's iodine dissolved in alcohol. It's actually a solution. That's a very common mistake students make on the test because they always have that idea of iodine being in the iodine they've seen is the one that's dissolved in alcohol. Tincture of iodine. Okay. So what was the answer to that one? Oops, okay, D, iodine solid. What about this? What's the delta H formation? For which of the following is the delta H formation equal to 0? Carbon gas, carbon graphite, carbon diamond, or carbon or C60? I'm going to give you a chance to change your answer to the correct one since this is really trivial information, but you really should have learned this in your earlier class in Chem 1, so 105. It's the lead in your pencil. It's a solid. Graphite. Okay. Graphite is the most stable form of carbon under ordinary conditions. Okay? So that diamond in your ring, okay, millions of years from now, you can use it as a pencil. Okay. All right. Standard reaction enthalpies are easily calculated from tabulated values of standard enthalpies of formation. Okay? So why is that? It's really just an application of Hess's law. Imagine your reactants, change it to elements in their standard state. What would be the delta H for that? That will just be the negative of the delta H formation of your reactants. Why? That's just the opposite of making it from the elements, right? Okay. Now imagine the elements in their standard state now. Change them to products. What's the delta H for that? That's just the delta H of formation of the products. You're making it from the elements in the standard state. And you have to add it up for all the reactants and add up all the numbers for the products. So if you combine this equation and this equation, these two reactions, what do you get? You have the overall reaction where you have reactants end up as products. So what's the delta H for this overall reaction? The sum of these two. So negative delta H formation of reactants plus delta H formation of the products. Or you can say delta H formation of products minus delta H formation of the reactants. Okay? So that's the beauty of tabulating standard enthalpies of formation. You just need, for any reaction that you have, you just look up the standard enthalpies of formation, then you just take products, the values for the products, subtract the values for the reactants, you get the delta H for the reaction. All right, so let's illustrate that with an example right here. Let's say you look at the delta H formation of the reactants and products involved here, and they happen to be W, X, Y, and Z. What's our delta H for the reaction? It's delta H formation of the products, right? Minus delta H formation of the reactants. So what would it be for products? Y plus 2Z. Why 2Z? 2 moles. Because the numbers I have given here are kilojoules per mole. Okay? Minus reactants would be W plus 2X. Okay? Can I simplify this? Y plus 2Z minus W. Like that. Y. What is X? This is O2 gas. That's an element in its standard state, so that is 0, right? So where can we find these values? You should be able to find these delta H formation in tables at the end of your book. Or you can look it up on the web. A good source of these values would be webbook.nist.gov. So let me show you where you can find that. webbook.nist.gov. Okay. So when you get there, click on NIST Chemistry Webbook, and you can do a search for a formula. For example, if I want to know CO2, carbon dioxide, I want to know delta H formation. I want thermodynamic data for the gas phase. So I just check that box right there. I hit search, and I'll find here, okay, delta H formation of carbon dioxide is negative 393.51 plus or minus 0.13, and the units here, is kilojoules per mole. Okay, and it gives you the reference, primary reference for that value. Okay, so you may see several values from different sources. So that's a good source of information. Heat capacity also, you can look it up in case you needed it. Heat capacity actually in general depends on temperature, and so this is the formula that you can use to calculate the heat capacity per mole. And you have some constants that you can plug into that equation right there. Okay? So that would be a good source for finding delta H of formation values. Okay. How about this one? Let's say you have this reaction, benzene, C6H6, plus O2. The coefficient here is 15/2. Okay, gives you 6 CO2 gas plus 3 H2O liquid. Let's say you found the delta H for that to be delta X kilojoules per mole. Okay, this is something you can easily measure in the lab. Okay, combustion reactions are the kinds of reactions that are easy to measure in the delta H for those are easy to measure in the lab. Okay, we just talked about that earlier. All you have to do is burn the material and you can get your delta H, right? So this This is something you can easily measure. Now, delta H of formation of CO2, you can look that up from, okay, from tables at the back of your book or from the internet. And delta H formation of liquid water, so that's also something you can easily look up. So let's assume you know this value to be Z kilojoules per mole for water, and it is Y kilojoules per mole for CO2. Okay? This example illustrates how you can construct a table of delta H of formation. So you have an experimental data. From your experimental data, you can get delta H combustion. Now that you know delta H combustion, and suppose you've already established delta H formation for water and carbon dioxide, how would you get delta H formation of C6H6? So let's call the delta H formation of C6H6 to be X. What would it be? What would X be equal to? I'm sorry, that's not X. I'm sorry. X is this one, right? The delta H for this reaction. So let's say I want the delta H formation of C6H6. So let's call this W. How would I solve for W? So we say X is equal to the overall reaction. The delta H for the overall reaction equals delta H formation of products, which would be what? 6Y plus 3Z minus delta H formation of reactants would be W plus 15 over 2 times what's delta H formation of O2 0, element in its standard state, right? So can I solve for W? That's the coefficient of O2, 15 over 2. To balance this equation, you need a coefficient of 7.5 over here. Okay? 15 over 2 times 2, that's 15 oxygens on the left. On the right, you have 6 times 2 is 12, plus 3, that's 15 oxygens on the right to balance it. That's why you need that coefficient right there. Okay. So, now that you have that, I'll let you work it out and give me the answer. Is it A, B, or C? What is the delta H formation of C6H6? Solve for W, right? You got it? So X equals 6Y plus 3Z minus W. So how do I solve for W? C. Is that the right answer? W equals solve for W. W equals 6Y plus 3Z minus X. 6Y plus 3Z minus X. C. Very good. Okay. You can skip this one. I already explained where the Hesss Law comes from. For reactions in aqueous solution, as a matter of convention, the delta H formation of H plus is defined to be 0. Okay. Now, why do we have to make an arbitrary value for H plus? The reason is you cannot form ions individually in solution. They always come in pairs. So if you get the delta H formation of HCl aqueous, this is really H plus aqueous plus chloride aqueous. Okay, you can measure that delta H for that. That's, let's say it's X. Okay, since that would be the delta H formation of H plus ions and chloride ions. Okay, but they always come as, you cannot just have positive ions. They always come with negative ions with them. So as a matter of convention, for us to be able to tabulate a delta H formation for individual ions, we assign a value of 0 for H plus. So if in this case, the delta H formation of H plus is 0, what's the delta H formation of chloride? Here you're forming H plus and chloride from the elements in their standard states. Okay? So what does this mean? Delta H formation of chloride, in this case, would just be equal to whatever that X is, right? Because here, you can say delta H formation of H plus and chloride together is X. But as a matter of convention, we're going to assign this a value of 0. So delta H formation of chloride there, then in aqueous solution, is the same thing as the delta H formation of HCl in aqueous solution. Here you have sodium chloride, okay, aqueous solution. You're forming it from sodium solid, that's sodium in its standard state, so that's element sodium in its standard state. Cl2 gas is chlorine, the element in its standard state. You're making sodium chloride aqueous from sodium and chlorine in their standard state. So this delta H here would be what? The Y that you have here, based on this information right here, you can say that the delta H formation of sodium plus the delta H formation of chloride must be equal to Y. Okay? So when you're dealing with aqueous solutions, the delta H formation of a salt in aqueous solution is just the sum of the delta H formation of the ions. So based on that, what would be the delta H formation of sodium then? This is going to be equal to 1. We already identified this as X, right? So delta H formation of sodium is equal to Y minus X. This illustrates how you can construct a table of delta H formation for the ions. And the value of being able to construct this table, so you now have this table that has all the delta H formation for the ions, is if you have a salt in aqueous solution, all you have to do is add up the delta H formation of the ions that you can look up. Okay? So let's look at this one. What is this first one right here? This tells you that the delta H formation of, you're forming HCl from its elements, right? So that's the delta H formation of H plus delta H formation of chloride is equal to X. What does this second one tell you? You're forming magnesium chloride in aqueous solution from magnesium, the element, and chlorine, the element. So that would be, the second equation says, delta H formation of magnesium ions plus 2 times the delta H formation of chloride ions. Why 2? Because magnesium chloride in aqueous solution is 1 magnesium and 2 chloride ions, right? So that must be equal to Y in this, if the delta H for this reaction is Y. Can I solve for the delta H formation of magnesium in terms of X and Y? What would it be? Is it A, B, or C? Remember we said, what is this one? H plus is 0. Can I solve for delta H formation of magnesium based on this information? You ready? What does this tell you? X is just equal to delta H formation of chloride. So where would you plug the X? Right there. So this thing is just X. So what's the delta H formation of magnesium? It's just equal to Y minus 2X. Okay? So you can say here that that's delta H formation of magnesium ions in aqueous solution plus 2X is equal to Y. So you subtract 2X from both sides. So it's Y minus 2X, the answer. Let's take a look now at the molecular interpretation of reaction enthalpy. When a reaction occurs, you need energy to break existing bonds and you need energy to form new bonds. So if you were to monitor potential energy as a reaction progresses, what would happen? Potential energy would increase, right, to break the bonds, and it would decrease to form when bonds are formed. Okay, so if this level right here involves all bonds being broken, then that's what happens. But in general, that's not the actual path that the reaction takes. A reaction doesn't necessarily mean that bonds get broken first and then bonds get formed. Okay. During a reaction, what could happen is there could be partial breaking of some bonds and partial formation of some bonds. You get what's called a transition state, or in my form also intermediate states. So you have that transition state, and so the real process would not involve as much energy as you don't necessarily have to break the bond. So this might be the energy you need to break the bond. The reaction may not require that much energy to get it going. So this minimum energy that the reaction needs in order for it to occur is called your energy of activation. Okay, so but the delta H you calculate, which is the difference, which can be just approximately the difference between the potential energy of the reactants and the products. Okay, that is that is a state function. Enthalpy is a state function. So it doesn't matter if you imagine breaking all the bonds first and then forming the new bonds. Okay, you still get the same delta H. So energy is needed to break existing bonds. Energy is released when new bonds are formed. So bond breaking, okay, you need energy to raise the potential energy, and then bond formation, you release energy. So your potential energy becomes kinetic energy. So if more energy is released, then the extra energy just becomes kinetic energy of the products and the surrounding molecules, and your temperature increases. You say your reaction is exothermic. So this would be an exothermic reaction right here. Okay. So think of this diagram. Let me show you a better diagram. This would be the So if this was to scale right here is the progress of the reaction, and you have your potential energy here, reactants, products. Okay, this might be the kinetic energy right here of your reactants. Okay, once you get to the product side, if this is the kinetic energy of the product, this extra energy right here, okay, would have to be 1. That's released to the surroundings, so becomes kinetic energy. So the net effect is you have conversion of potential energy to kinetic energy if you have an exothermic reaction. Okay. Now, if you have an endothermic reaction, what would the potential energy profile look like? It would look something like that. Okay, so this difference right here would be your delta H. Okay, it would have to absorb energy from the surroundings in order for it to produce products at the same temperature. So if this was the kinetic energy of the reactant and you want the product to have this much kinetic energy as well, Okay, then this difference right here, which is going to be essentially this difference, would be the amount of energy that has to flow into your molecules, into your atoms, in order to convert your reactants to products. That's the molecular interpretation of heats of reaction. Okay. So classify the following as endothermic or exothermic. And what would be the algebraic sign of delta H in each case? Let's look at the first one. What happened there? CH4 gas breaks up into carbon atoms and 4 hydrogen atoms for each CH4 molecule. Exothermic or endothermic? What's the only thing happening there? Bond breaking. So delta H is positive or negative? Positive. Positive. It's endothermic. This process, for this to happen, you have to be providing it with energy from the outside. How about this one? Delta H for this. Two iodine atoms forming an I2 molecule in the gas phase. This is an exothermic reaction. Okay? A third body has to carry the energy away in order for your two iodine molecules to get stuck in a bond. Okay? It's an exothermic reaction. How about this one? 2I gas to I2 solid. Even more exothermic, because now to get your I2 gas to come together closer to each other to form a solid is also exothermic. That would be the opposite of sublimation, which is also exothermic. So delta H for this is also negative. This is also an exothermic reaction. Okay. What time do we have? Okay, got plenty of time. Bond energies or mean bond enthalpies can be used to estimate delta H of reaction for gas phase reactions. Okay, so for example, H2 plus Cl2 gas gives you 2 HCl gas. You can calculate the energy needed to break one HH bond, and then the energy needed to, you can look these up, okay? The bond dissociation energy to break one Cl-Cl bond, and then if we define Z as the energy released when HCl bond is formed, then delta H for this reaction is just X plus Y minus 2Z. Why is that? This is the energy needed. So if X, Y, and Z are just absolute values, these are positive numbers, okay? So this is the energy needed to break the HH bond plus the energy needed to break the Cl-Cl bond. How many HCl bonds are you forming here? 2, right? So minus 2 times the energy needed, energy released when an HCl bond is formed. So there's a negative there because bond formation is exothermic. So it's really just the sum of the bond energy for dissociation, for bond breaking, right? Sum of the bond energies for breaking bonds minus the sum of the bond energies associated with the bonds that are formed. So bond formation. So this works really well for gas phase reactions for estimating. So let's look at this. The reaction enthalpy can be estimated using bond energies for which of these reactions? A or B? What's the difference between these two reactions? This one's a liquid and that's a gas. Everything else is the same. So what's the answer? Bond energies, you can only use that to estimate delta H for gas phase reactions. Everything in the gas phase. Okay, so answer is B. Which one? This one? This is all gases. Oh, that's because, because you know that if you want to go from gas to solid, that it's going to be exothermic as well, right? And we're just predicting algebraic signs, so we're not actually calculating. What I'm saying here in the case of bond energies, you can actually calculate because you can look up these bond dissociation energies. Okay, these can be it's experimentally determined. Actually, what's done is you experimentally determine this. The numbers you look up is actually just an average for these bonds as they are found in different molecules. And so that's why it's an estimation, because it's not always going to be the same. For example, in a CH bond, when you're doing CH4, okay, if you break the first CH bond, okay, that will take a different amount of energy as opposed to breaking the second CH bond. Let's see. So you're gonna get CH2 here. Okay. That's the second CH bond will have a different, and you'll need a different energy. It'll require a different amount of energy to break as opposed to the first CH bond. So the numbers that you actually found tabulated as for bond energies for estimation purposes, those are the average of these 4 CH bonds. It's not really just these 4 CH bonds. You have a whole series of different molecules that it's based on. So that's why they're really just estimates. All right, so let's consider this reaction right here. Methane plus oxygen gives you CO2 plus 2H2O. Okay, let's say we've looked up the bond energies to be W for CH bond, X for a double bond between 2 oxygens, Y for the double bond between carbon and oxygen, and Z for an OH bond. What's the delta H for this reaction in terms of W, X, Y, and Z? Okay, so how many CH bonds would you have to be breaking here? 4, right? Your methane is CH4. You have 4 CH bonds. So you're gonna have to need your delta H will have to involve a term that says 4W, right? So you can eliminate choice A and B right away. But let's finish this up anyway. Let's verify that C is in fact correct. Oxygen. How many oxygen bonds would you have to break? What's the lowest structure for O2? So that's 1 oxygen-oxygen double bond, and you have 2 of those. So you're going to need 2X, right? So this is the delta H for bond breaking. Okay, what would be the delta H for bond formation? Okay, how much energy would be released in forming carbon dioxide? What's the lowest structure for carbon dioxide? You got 2 C double bond O's. So how many CO bonds are you forming? You have 1 CO2, so 2 CO bonds, right? 1, 2. So that's going to be 2Y would be released, so you have to put that as negative 2Y. So minus 2Y. And then how many OH bonds are you going to form? What's the structure for water? HOH. How many OH bonds? 4 total. That's you got 2 water molecules. So you have HOH. So you have 1, 2, 3, 4 OH bonds. So 4Z. Okay. So OH bond energy is Z. So minus 4Z. So that would be your estimated delta H for that reaction.